Hi, welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. So in this class, we'll talk about camera models. So let's start with pinhole camera model. So imagine you have, let's say, infinite plane, and you have a very tiny pinhole. So when I say very tiny pinhole, literally it's a point. So this is your object. Your object sends the rays from the top and from the bottom, and it's projected on a plane which is known as the image plane. And notice that this image is inverted when you see it in the picture. So this is how the normal camera works as well. So whatever your object is, it's projected inverted, and through software or something we invert that image back. So in real world, these approximation of pinhole doesn't work, because when you go with the tiny aperture like pinhole, there are things called diffraction. So any light ray that is entering the pinhole, basically if it's too small, it will hit the edge of the hole, and through diffraction your image will be very blurred. So the diameter is directly proportional to the square root of the focal length and the wavelength of light. So you can write that d equals 2 times under root f lambda. So although smaller pinhole radius leads to diffraction, but you can use formulas like this. But again, pinhole model doesn't exist. So in real world, rather than having a pinhole, you have a convex lens. Okay, and notice that this f is the focal length for this camera. Okay, moving on. So let's see how a pinhole camera model works. So you have a point P in space. This is a 3D world point, which is denoted by capital X, Y, Z. So in computer vision, when I talk about capital X, Y, Z, it's always in 3D world coordinate system. When I talk about small u, v, or small x and y, it's in a projected schema or on the image plane. Okay, so my point P, real point P, X, Y, Z, is you have a center projection point O. It's projected on the image plane. So you saw in the previous one that this is the virtual image and this is the image plane. So these are identical. You notice that the only difference is in inversion. So in this slide, we are talking about the virtual plane. So whatever your 3D world point is, that will be projected on this virtual plane at point PC, and the the position of this point PC would be u comma v. So if I use similar triangles, I can say that this focal length upon the total depth f by z equals u by x and v by y. So I can just compute u equals fx by z and v equals fy by z, and my w, if I want to call u v comma w, that will be 1. Okay, so I can write my uvw or uv1 as ff0 and ff1, and you have zeros here, right, and multiplied by my x, y, and z. So I'm just converting this into a matrix formula. That's it. These two are same equations. So this equation assumes that my 2D image coordinate system coincides with the center of projection O. Right? This might not be the case. The center of projection might be somewhere here, somewhere here. It might not be exactly at the center due to manufacturer defect or something like that. Also, to make sure that this is called center of projection, and my axis that joins O to the axis perpendicular to my image plane, it's called principal axis. Okay, so coming back to the point, that O need not be at the center because of some manufactured defects, right? So it can be shifted. So let's say it's shifted by Cx in the x direction and Cy in the y direction. So my O is somewhere here, right? So it's an offset. So I can say that my U equals fx by z plus cx and v equal to fy by z plus cy. So I can rewrite my equation replacing zeros in this by cx and cy. So these are also called as principal points. So this is my new equation, given that my center of projection is not exactly at the center, right? So one more important thing is this assumes that my focal length is different in is same in x and y direction, which might not be the case. My lens might have a different focal length in x direction and different focal length in y direction. In practice, these are similar. So let's say, for example, value of fx is 100. The fy would most likely be somewhere between 95 to 105. So, but in real world, they are not exactly same. So you'll have fx, fy, cx, cy, and this would be the new equation, right? But this thing also assumes that there is no shear distortion. But when you take an image, you see a bit of shear distortion in the projected image, right? So I need a term called S, which is my shear. This is a measure of the shear. Shear means basically if I have an image, how much it's tilted in this direction or this direction. That's what shear is. Like you take an image, you pull it from one side. That's what axis skew or shear means. Okay. So P is my 3D world point, PC is my projected coordinate system or projected center, and this matrix that you see here, which which has my focal length, principal points, and skew. This matrix is called as K matrix, which is also known as intrinsic parameter of a camera, and it's a 3x3 matrix. And note that it's always an upper triangle matrix. Okay. So moving on. So this is called a projection equation, where let's forget lambda and r and t for now. So uv equals k xyz was the equation we saw before, right? R and T is basically if I have, let's say, 2 frames, right? So I want to compute the rotation and translation. Let's say if I already know the rotation and translation between these two. So I know the world coordinate xyz, I know the rotation and translation between 2 frames, I know my intrinsics, then only I can compute my projected points u comma b. So this entire equation is called a projection equation. And you see this lambda over here, this is a scaling factor. So this is because this point P in space can be anywhere on this line, right? So I have no idea if my point is 1 meter high and 0.5 meter away, or 2 meter high and 1 meter away. My projection on the image plane at that point will exactly be the same. So if I don't know anything about the object or how far the object is, I would never know anything about the object. So I need at least one thing. I need to know either how far the object is, or I need to know how big the object is, for example. So that is what this lambda scaling factor will give you. You can't have it from magic. You need a scaling thing to know about the scene, basically. Okay, coming back to R and T, which is rotation and translation between the frames. So this is also known as extrinsics, because it doesn't depend on your, for example, lens and how it is placed with the camera. Extrinsic is basically between 2 consecutive frames, or 2 frames in general, or it can be anything. Extrinsics can be between a frame of, let's say, a camera and another camera frame. It can be between a camera frame and an IMU. It can be between one IMU data to the other IMU data, which are placed with a distance and a rotation between them. Okay. So this mapping of 3D coordinates of points in space to this 2D image coordinates is known as camera projection equation. Okay. So the thing we were talking about before was, this is a pinhole, and this and the camera lens that your camera phone, or in general any professional camera has, is the same. Basically, the way it's being projected, you will get that focal length f, and rather than having a pinhole with the minor transformations, you will basically have this camera lens and you'll get the same output on the image plane. Okay. So how do we calibrate these intrinsics? So what you have is the general, you have a, let's say you have a printed board. Let's say you printed a pattern like this. So let's say you have in this case 7 cross 5, I believe, 7 cross 5 squares of known width. Let's say this width is, let's say, 15 millimeter. So I know this before, right? I have, when I'm calibrating the camera, I will make sure I input this in my whatever algorithm, whatever calibration algorithm is. So the first step is to detect these corners. So at a given angle, I will detect all these corners. So this, once I detect this, I know that distance between these two is 15 millimeter, distance between these two is 15 millimeter. Same thing, distance between these two is 15 millimeter, distance between these two is 15 millimeters, right? So what I'm gonna do is, not just with this frame, I'm gonna take images from multiple translation and multiple orientation, and I'll try to have as many combinations as possible. I do not want like 500 or 1000 of these images, but I definitely do like to have about 20 to 30, 35, 40 images, something like that. So you have a good enough estimation for your calibration. So the reason being, you don't want 1 or 2 images, because once you have like these 30, 40 images, you have, from each image you are trying to calibrate K, right? From a set of images you are trying to calibrate K, but that won't be perfect because your camera will have some issues, like intrinsic issues when you're calibrating. So what you want to do is, from multiple frames altogether, you want to optimize for all the calibration parameters like focal length and my skew and CX and CY with the principal points all together at once. So that's why you take like 30-40 images. If I take like 500,000 images, my optimizer will be very slow and it's not required in general. So rather than these checkered board that we saw in the previous case, there are other types of calibration board that you will see in day-to-day life. One of them is like a Ruko marker. So each of these marker, when there's, rather than having just a white spot, these markers have some special type of pattern, like each pattern is different from the other, so it uses that. This is another set of calibration which is a little better than checkerboard, depending on how good your checkerboard is. Again, one more important thing to note is, your calibration basically depends on how accurate your printing is. Let's say you printed a checkerboard on US letter size versus you printed a checkerboard on, let's say, 10 meter by 10 meter huge checkerboard. You will get much more accuracy on 10 meter by 10 meter. Another thing to understand is, when you're printing these checkerboard, make sure you're not scaling them. So when you're printing, there are options that scale to or fit to page or something like that, right? That might when you're printing that, rather than having square, you might have rectangle, and you don't want that, right? So make sure when you're printing these things, your measurements are accurate. And once you have that, take a caliper and try to measure the exact length of the square and check if it's correct or not. Okay, moving on. This is one of the Ruko markers, and this is another pattern which is circular pattern, and people use that because you are trying to estimate your pose from these multiple circles from different views. This is another calibration board basically. Okay, let's talk about extrinsic calibration, which is basically RNT that we discussed. So R is rotation matrix, which is 3x3 matrix, and translation is your relative translation, which is TX, TY, and TZ, which is a 3x1 vector. And together, extrinsic calibration matrix, if you want to call it, or extrinsic matrix R comma T, is a 4x4 matrix. Okay, so this can be between a camera and an IMU, like your phone in general. If it's, so let's say there are a lot of phones which are capable of doing visual inertial odometry. So odometry basically means to understand your pose of something, like how am I moving relative to the scene. When I say visual odometry, I'm using only the camera information to understand where am I and how my movement is going through a different set of frames. So if I'm at this point and I'm moving like this, so there's a path like this, right? So this is my path, and the way I'm measuring is just using a camera. And if I can redraw that graph using a camera, it's called visual odometry. And if I'm using inertial sensor for doing this, it's called inertial odometry. When I'm fusing these two sensors, the camera and the IMU, it's called visual inertial odometry. But to do that, okay, before that, there's one more thing to understand, that we discussed that we cannot get scale using visual odometry, right? So I don't know if I moved 1 meter or if I moved 1 centimeter, but I would know that this is the path I moved, right? So this is the benefit of inertial sensor. We can get the scale in inertial sensor because my gravitational vector and my omega are in actual real units, right? So fusing camera with inertial sensor, it's called visual inertial odometry. So once we fuse it, we can actually know the path to scale exactly how the camera or how the mobile phone is moving. But before getting that, I need to know my extrinsics between camera and the IMU of my mobile phone. So to do that, I need to know my relative rotation between camera and IMU and relative translation between the camera and IMU, right? To do that, I basically will calibrate my extrinsics again using something like checkerboard, and basically gain my extrinsic or RNT. So we discussed about in class about caliber package by ETH. So you can follow that how it works. You can read the paper if you want. So caliber is based on a series of 3 or 4 papers. So each describe one of the methods of the other. So next is stereo calibration. So in this, let's say you have 2 cameras, and because you have 2 cameras, you can ideally estimate depth of a scene that is in front of you. We'll talk about how stereo camera works later on in this course, but for now, understand this. To know the actual depth or to get the scale, what you want to do is you have one camera, you have the second camera, both can do visual odometry, but both alone will not be able to tell the unit. They don't have a scale, right? So the scale you are gonna get is from the relative distance and rotation between two. So if you have a relative RNT between these 2 cameras, you can ideally get the scale out of it. So using checkerboard again, we'll calibrate using packages like caliber, the relative rotation and the translation between the camera centers of my camera 1 and camera 2. So again, go through caliber, go through these papers if you want. Don't worry about how stereo works for now, but understand that you need to know RNT between a stereo pair to know the scale of the system or know the scale of your odometry. Okay. So pinhole model we talked about doesn't talk about much distortion, right? But when we widen our field of view, let's say wide angle camera or fisheye camera or omnidirectional cameras, right? So the problem is my radial and tangential distortion affects my system a lot. So you can see in image A and B, like I'm projecting this up on a plane, right? In this, I am projecting what is getting from something spherical on an image plane, which basically has a lot of radial and tangential distortion. So if I want to write my distortion, it will be something like 1 plus k theta square plus k2 theta raised to power 4 plus k3 theta raised to power 6 and so on. So my tangential, as my angle or field of view increases, these factors from k1, k2 can go to k6 or k7, something like that, right? So this is called rad-tan model or radial tangential model, that how these parameters affect my wide field of view cameras. Okay. So this is an original image that you take from a fisheye camera, for example, and once you have these calibration, the K matrix and these distortion calibrated, both radial and tangential distortion parameters, you can basically undistort this image into this image. So this is a well undistorted image using a well calibrated parameters of a fisheye model. Okay, so the last but not least is color calibration. So people have facing problem with leopard imaging cameras, how to calibrate these colors. So the one way you can do it is probably take a photo and maybe move in Lightroom, and it has Lightroom is a software by Adobe, or you can even use MATLAB. They have color calibration methods. So what they do is they have these pattern. So if you have color calibration board, something like this lying around, you can take a snapshot using a leopard imaging camera, and it'll tell you, okay, my red channel needs correction of this much, my green channel needs a correction of this much, and my red channel needs a correction of this much. So you can use that and basically understand, is your red actually red or is your blue actually blue. So this is how you calibrate the colors if you want to do it. Okay, so that's it for today, and we'll discuss about transformation, projective geometry, affine transformations, and things like that in the next class. Okay, good luck, have fun.